Welcome to Career Campus Pro. Today we are diving into two most popular ways to represent a graph in programming. Choosing the right one according to the type of graph makes our code run faster. So let's start with the adjacency matrix. An adjacency matrix is a square matrix used to represent a graph. Each row and column corresponds to a node in the graph. The value at matrix ij represents the weight of the edge between node I and j. If there is no edge, the value is 0. Now let's create the nodes of our graph. Each node is represented by a circle with a label inside. As we add each node, we will also prepare the adjacency matrix structure in background. The matrix is initialized with zeros, indicating no edge between the nodes. The rows and columns are labeled from 0 to 3, corresponding to our nodes. As we add the edges, we will update the matrix to reflect the connections. Now let's add edges to our graph. Each edge has a weight which we will represent in the matrix. For example, when we add an edge between 0 and 1, the weight of 5, we will update both matrix 0, 1 and matrix 1, 0 to 5 since it is an undirected graph. So the matrix is symmetric. Similarly, we will add all other edges of the graph with their corresponding weight associated. Now let's demonstrate how to delete an edge. We will remove the edge between node 1 and 3. When we do this, we will set both the matrix 1, 3 and matrix 3, 1 back to 0. This shows there is no longer a connection between these nodes. Let's implement an adjacency matrix in Python. We define a class called graph. In the constructor, we initialize an empty matrix and populate it with zeros based on the size of the graph. We also store the size of the graph to manage operations efficiently. So now let's move on to adding edges. The add edge method allows us to add edges between nodes with an optional weight, and we update both the matrix ij and matrix ji for undirected graphs. In the remove edge method, if an edge exists, we reset its value to 0, effectively disconnecting the vertices. Similarly, in the remove node method, it removes a row and column from the matrix, effectively deleting the node and all its connections. To visualize the adjacency matrix, we provide a function to print its values row by row. Additionally, we can retrieve the edge weights effectively using a simple lookup function. Now let's summarize the key points about the adjacency matrix. The time complexity of adding and removing is the order of 1. Space complexity, it requires order of v squares space, which is optimal for the dense graphs. And the adjacency matrix supports quick lookups, but they are inefficient for sparse graph. They allow weighted edges with constant time retrieval. Now let's move on to the adjacency list representation. Adjacency list is a collection of lists used to represent a graph. Each node in a graph has a list that stores its connected neighbors. Here we consider the edges with undirected graph with the corresponding weights. Empty list means no connections. It uses tuples to store edges along with their weights. First, we will create the nodes of our graph. Each node is represented by a circle with a label inside. Next, we will create the structure of the adjacency list. Each node's list is initialized as empty, indicating no connections yet. As we add the edges, we will update these lists to reflect the connections. Now let's add our edges to the graph. Each edge has a weight, which we will represent in the adjacency list. For example, when we add edge between 0 and 1 with a weight of 5, we update both node 0's and node 1's list to include the connections. Because this is our undirected graph, so connections appears in both lists. Similarly, all other edges between all the nodes with their corresponding weights are added as the tuples. Now let's demonstrate how to delete an edge. We will remove the edge between node 1 and 3. We remove the entries both from the node 1's and node 3's list. This shows that there is no longer a connection between these nodes. Now let's delete a node. We will remove node 2 and all its connections. When we do this, we remove node 2's list entirely and update the list of its neighbors to remove any reference to node 2. This ensures the adjacency list remain consistent. Alright, let's implement an adjacency list in Python. We will start by defining a graph class. The constructor initializes an empty dictionary for the adjacency list. In the add node method, we simply check if the node exists. If not, we add it with an empty list of neighbors and increment the number of nodes. Now, the add edge method handles both new edges and updating the existing ones. First, we ensure both nodes exist or not. Then we check for existing edges between the nodes. If an edge exists, we update its weight. If not, we add new edges in both directions since it's undirected graph. We use the enumerate to track the positions of its neighbor list. The else clause after the for loop handles the new edge creation, and we maintain the symmetry by updating both directions. Further, moving on to the removal operations. The remove edge and remove node methods use Python's list comprehension for clean, efficient operations. First, we remove all the references to it from the neighbors, then delete the node itself, and finally update the node count. And our printList method gives us a clean way to visualize the graph. So let's summarize what we have learned today. It's having the time complexity of order of 1 for adding nodes, space complexity of order of v plus e. It is suitable for sparse graph and efficient for neighborhood queries, faster iteration over the edges. I hope you enjoyed the video. Don't forget to like and subscribe for more videos on DSA. Happy coding. Thank you.